where we left off last time, we had just introduced chemical reactions and the idea of balancing chemical equations. That's what I was suggesting, Angela. So what we haven't done really is kind of get into the nuts and bolts of balancing. It takes a little bit of time to do some balancing, at least get to the point where you're comfortable enough with chemical reactions and balancing chemical reactions that you can do it without a list. We talked about, we did a couple examples that were quite simple. And ultimately what you need to be able to do is you need to be able to balance them in a way that actually you can do it pretty quickly. And so I wanted to start off with just a couple of examples, but then I wanted to move on into some more complicated stuff and kind of go from there. So let's do something real quick that's a little bit easy. We'll do CH4. This one isn't going to have any state symbols because that's not what I want to worry about right now at the moment. But let's take a look at something like this, okay? So you can get into the habit of writing down a list of atoms. But what I was saying was that this is certainly helpful for you in the beginning. Ultimately, you really do need to be fast enough that you don't need this list, okay? And so you really do need to be that fast. And we'll use the list this time and maybe one other time, but I'm gonna start to move away from that list because at the end of the day, with enough practice, you should be able to do it without it. But the list does help to start with, to kind of give you an idea of how many atoms that you have, and helps you in the practice of counting. Okay. So we see that on the left we have 1 carbon, 4 hydrogens, 2 chlorines, and on the right it's 1 carbon, 1 hydrogen, and 5 chlorines. And of course, ultimately the goal is to get the list to be the same. So I'm going to give you a couple of different rules, and they're not rules, they're more like suggestions. And so we'll go over these suggestions and we'll build up this list of suggestions as we go along. The first suggestion that I had was balance non-hydrogen, non-oxygen atoms first. And the next one is I'll save elements until the end. And what I mean by an element is, of course, something like Cl2. That's an element. And the reason that you save it till the end is that if you put a stoichiometric coefficient on chlorine, the only thing that it affects, or Cl2, excuse me, if you put a stoichiometric coefficient on Cl2, the only thing that it affects is chlorine. And so it doesn't affect other atoms in your counting. That's why we want to save it till the end. Now, in this particular case, the hydrogen is, we would start off saying balance non-hydrogen, non-oxygen atoms and save elements until the end. And so that means that would leave us with carbon in this example to start off with. But we see that carbon's already balanced, so we'll move on from that. We'll still want to save chlorine until the end. So let's take a look at the hydrogen situation. Well, I've got 4 on the left and 1 on the right. So I need to change that so that I now have 4. So if I put a stoichiometric coefficient of 4 in front of hydrochloric acid, then I get 4 hydrogens. But now you can see that I've changed the count for Cl. I've got 1, 2, 3, 4 in CCl4, but now I added another 4, so the total is now 8. The total is now 8. And so this, now I can go back and do chlorine at the end. I can add a stoichiometric coefficient of 4 there, and that'll get me the 8. That's what I mean by that. Let's do another example real quick. I'll use the list one more time, but that'll be the end of it. All right, let's do PCl5 plus water produces H3PO4 plus HCl. Okay, so I've got phosphorus, I've got hydrogen, I've got chlorine, and I've got oxygen. I've got phosphorus, hydrogen, chlorine, oxygen. Here I've got 1 phosphorus. Total looks like I've got 2 hydrogens. Looks like I've got 5 chlorines and 1 oxygen. Looks like I've got 1 phosphorus. I do have a total of 4 hydrogens. Remember, you have to count them from both sides, or from both molecules in the equation. And I've got 1 chlorine, and I've got 4 oxygens. So let's try to apply those rules now. Let's do non-hydrogen, non-oxygen atoms first. We'll save isolated elements until the end. It doesn't look like there are any isolated elements in this case, so I won't even apply that particular suggestion. So I will start off with non-hydrogen, non-oxygen atoms, and that leaves phosphorus and chlorine. It looks like phosphorus is already balanced with 1 and 1, so let's move on to chlorine. I've got 5 on the reactant side and 1 on the product side, so in order to balance the chlorines, I would add a 5 there. So that changes that count to 5, but it also now changes the hydrogen count. So what you're doing is you're going back every time you add a stoichiometric coefficient, and you're rechanging everything. You're recounting everything. So I still 1, 2, 3 hydrogens from the H3PO4, but now I have 5 HCl's, so that's a total of 8 hydrogens. Okay, so now I'm doing the hydrogen and oxygen atoms. And so let's deal with hydrogen since I just changed it. It looks like I have 8 on the right and 2 on the left. So if I use the stoichiometric coefficient of 4 there, I'll have 8 hydrogen atoms. But now I did change the oxygen. I went from 1 to 4. And it looks like we're good now. So that one move, that one stoichiometric coefficient, did everything I need to do in order to balance the equation. Okay. We're going to do a lot of examples. So let's go ahead and move on. Let me introduce the combustion reaction. There are very few types of reactions that you have to know how to complete. One of them is the combustion reaction. And the general idea of combustion is fuel plus oxygen produces water and carbon dioxide. So often you could all I might give you is the fuel. I might say something like CH4 is burned. So that's a combustion. Or C2H6 is combusted. So I might only give you the fuel, and your job would be to fill out the rest. So to use CH4 as the example, I might say balance the combustion reaction of CH4. So you would write down CH4 plus oxygen produces water and carbon dioxide. Does it matter if I list carbon dioxide before water? Definitely not. Definitely not. The order doesn't matter. It's just what side of the reaction matters, whether it's a product or a reactant. And so let's get into this situation now. So I have starting with non-hydrogen, non-oxygen atoms, I have one carbon on each side, so they're good. I'll do hydrogens next because non-oxygen, hydrogen atoms are done, and I'll save oxygen till the end because it's a pure element. So I have 4 on the left and 2 on the right, so adding the stoichiometric coefficient of 2 at that location will balance the hydrogens. So I have 4 with CH4, and now I have 2 waters, and so that brings the total hydrogens to 2. Now let's count oxygens. I have 2 oxygens on the left, and I have a total of 2 waters, which brings 2 oxygens, and I have 1 carbon dioxide, which brings 2 oxygens as well, for a total of 4. So how do I make this a total of 4 on the left? Well, a stoichiometric coefficient of 2 will work out for me there. So now I've balanced the combustion reaction of CH4. Let's keep doing this. I want to do a few more examples of combustion because combustion will bring up another common scenario, and I'll have a situation for you. I'll have a suggestion for you there as well. Let's take a look at C2, H6, as a fuel, and let's burn that. This is ethane. CO2 and water are the products, as usual. That's all the products will ever be in a combustion reaction. Okay. So let's start off with the non-hydrogen, non-oxygen atoms. That's carbon. I've got 2 on the left, 1 on the right. You should be getting to the point where you're counting pretty quickly. I've now balanced carbon by making 2 carbon dioxides, and so let's take a look at the hydrogen. I've got 6 on the left and 2 on the right. So if I add a 3 here, then I'll have balanced hydrogens, giving me 3 waters. 3 times 2 is 6 hydrogens, 6 in the original ethane. I'm in good shape there. Now let's go ahead and list the oxygens. I have 2 oxygens here. How many oxygens are on this side? I've got 2 CO2s, so that's 4, plus 3 waters, that's 7. So this introduces a common situation. Take a look at the situation here. It doesn't matter what I do with the stoichiometric coefficients for oxygen. I can only get even numbers on the left, and I have an odd number of oxygens on the right. So let's try 1. That was understood. That's what I started with. If I have 2, then I move up to 4. If I use 3, then I move up to 6. And if I use 4, I move up to 8. So I can't, right away, I can't seem to balance oxygen without doing something weird. And so what if I do a 5? Well, I hope that you're good enough at math that you know that 2 times 5 is 10, and that's still not 7. Once I went past 7, we've never added. We've never added, right? So we're not adding because that's not how this works. So don't change the rules on me there. So the suggestion was made, and this is actually how you do this. What I call this situation is the even-odd situation. It's a situation where it doesn't matter what you do, you get into an even-odd situation. I'm even on this side with every stoichiometric coefficient, and I'm odd on this side with every stoichiometric coefficient. Sure, we can go back and we can change this to 6, but that now changes my hydrogen count. I'm now at 12, so I got to do that too. And so what it's going to do is be a cascading effect. So let me back up, because that's really where we're heading, right? So when you're in an even odd situation, multiply everything by 2. The trick is to identify that you're in an even odd situation. So it's whenever you find that you can't balance an atom because you need odd atoms on one side, but you can only get an even number on the other, that's an even odd. If you're in an even odd situation, multiply every stoichiometric coefficient by 2 and recount. So 4 and 6. So now we have 2 times 2 carbons, that's 4. 4 times 1 on the other side, that's 4. 2 times 6 hydrogens, that's 12. 6 times 2 hydrogens, that's 12. We're good there. So now what do we do? What are we into with oxygen? On the over here we have 4, and now on this side it's 4 times 2, that's 8. And then 6 times 1 is 6. 8 plus 6 is 14. Now we're in a situation where everything's even, and I should be good at this point. So if I change the stoichiometric coefficient of 2 to 7, then I get 14, and now everything is balanced. So one of the last tricks is the even odd trick. If you find yourself in even odds, you can multiply everything by 2. Now, one thing you could have done is the following. You could have said, what about this? What about this? How about using a fraction? How about using a fraction? Would this one have been okay? Is it okay to use fractions as stoichiometric coefficients? Okay, it doesn't have to be a whole number. It's okay to use a fraction. It's okay to use a fraction. What happens, though, is that you restrict the meaning. Nope, 7 halves does not equal 2.1. 7 halves equals, what, 3.5. Yeah. Mm-hmm. Yeah. It restricts the meaning of the sentence. Remember, this is a symbolic way to say a sentence. And the sentence is, without being balanced, CH2 reacts with oxygen to produce CO2 and water. But that's just a story that's not based in physical reality. In order to base it in physical reality, we have to use stoichiometric coefficients to balance the equation. If I use whole number stoichiometric coefficients, I have the broadest meaning in the symbology. I can say in the equation that I have starred, the one at the bottom, I can say 2 different ways. 2 molecules of C2H6 gets together with 7 molecules of water to produce 4 molecules of CO2 and 6 molecules of water. I can also say 2 moles of C2H6 reacts with 7 moles of O2 to produce 4 moles of CO2 and 6 moles of water. I can still say that with the equation above, with equation number 1. I can still say 1 mole of C2H6 reacts with 7 halves, or 3.5 moles of O2 to produce 2 moles of CO2 and 3 moles of water. But now I'm restricted. I can't use the first sort of way to describe it. I can't use molecules. I can't say 1 molecule of CH2 reacts with 3.5 molecules of O2. Why can't I say that? Why can't I say 3.5 molecules of O2. You can't have half a molecule, right? Exactly. Can't have half a molecule. If it's not the whole molecule, then it's not the molecule. I know I just said molecule 2 times really quickly in a row, but if it's not an entire oxygen molecule, if it's not O2, then it's not O2. It's something else. And that, remember, we can't just start adding species into the equation. And so remember, it's okay to use fractions, and you'll see that from time to time, depending on where you look. But remember, it does sort of restrict the meaning. Now, from a mathematical perspective, there's nothing wrong with it, and you can use the math, and it's fine. But who wants to use fractions in their calculations? I know that this is essentially middle school math, but still, we try to avoid fractions whenever possible, because they just complicate things. So if you get into the even-odd situation, use this trick, multiply everything by 2, and then balance from that point. All right, let's try another combustion reaction. Let's do C6 H14 plus O2 produces CO2 and water. Okay. So you got 6 carbons on the left, 1 on the right. Let's change that. Now I have 6 and 6. Let's recount the oxygens because that's what I just, or let's do the hydrogens. We'll save oxygen till the end because it's an isolated element. I've got 14 on the left, 2 on the right. Now I've got 7. So 7 times 2 with the water is 14. That's balanced. Now let's deal with the oxygens. I've got 12 plus 7, that is 19. And I've got 2 here. What is this situation? This is what I mean by an even-odd situation. The only thing I can get here are evens. The only thing I can get on the left, on the right are odds. So let's go ahead and use the little trick, multiply everything by 2. Since I'm multiplying everything by 2, all of the atoms except for oxygen are balanced. They're already balanced. So go ahead and convince yourself of that. And let's move on to oxygen. So I've got 12 times 2 oxygen here. That's 24. Plus 14 oxygen. I'm now up to, is that right? 38. Is it 16? Is that 16 times 2? Does that equal 38? No, it's not that. I think it might be 19. Is that right? I think it's 19. Yeah, all right. Good job, Eric. Way to use that advanced science degree. Okay, so that's really where I want to go with combustion reactions. There's another type of reaction that you need to be able to balance. And I want to use some basic symbols to talk about 4 different types of reactions. And I want you need to be able to identify them at the very least, and one of them for sure you need to be able to complete. So let's take a look. Let's do the first one. This one's very simple. Let's take something like this. And I'm going to use my colored symbols to describe this one. This is decomposition. Now, we can do the opposite of decomposition. And this is combination. So in the first one, it's decomposition. So you have one or more than one, as it were, it doesn't actually matter, species, and it breaks apart into more species. So you have less on this side and more on this side. That's decomposition. In this example, two things become one thing. In other words, more species becomes less species. That's combination. Remember, I'm not talking about the different colors correspond to the different elements, but I can use those elements to make compounds. And so if I have an element or a molecule that decomposes, decomposition, then it's going to break up. It's going to become more particles. If I want to combine particles together, then I have more particles that come together and form less. Yes, combination is the same as synthesis. Combination is the same as synthesis. Okay, let's try another one. Here's another one that you should be able to identify. This one is called single displacement. Single displacement. So in this reaction, one of the partners swaps. I don't think the word disintegration is used. I don't think the word disintegration is used. I think it's single replacement or single displacement. And I often forget what the word is because I'm so separated from it from way back. So single replacement or single displacement. Let me just look in the book. I want to make sure that I'm jiving with what Tro says. Yeah, no, the word is displacement in Tro. The word is displacement in Tro. Okay, let's take that same idea because I've got a single displacement and I also have double displacement. We're going to need a new color for that one, though. This one is, oh, sorry, missed out on your green, double displacement. Double displacement. So I taught you how to recognize a combustion reaction. I taught you how to complete a combustion reaction, and that's one of the reactions that you have to complete. And what I mean by complete is that you need to be able to predict all of the reagents and all of the products given some piece of information. So for a combustion reaction, if I give you fuel, you need to be able to write down oxygen as the other reactant and then the two products, CO2 and water. You need to be able to also complete double displacement reactions. And so not only do you have to recognize, but if I show you a reaction, be able to classify it as one of these four, but you also need to be able to complete a double displacement reaction. And let me give you an example of that. Let's have silver nitrate plus sodium chloride. How am I going to do that? So let's take a look. Let me color code it. There's black. There's blue. Here's brown. And here's red. So what does that mean? Well, that means that silver and chloride will come together, and sodium ion and nitrate will come together, and these things will form new compounds. It's not quite as straightforward as combustion because you know the formulas for the products, CO2 and water. You already know the formulas. With a double replacement reaction, a double displacement reaction, your job is to predict the products. And so that means you have to bring in your nomenclature, and you have to be able to write down the products of these reactions. And so what do I mean by that? Well, we have to know that it's silver ion and chloride ion that's going to get together. So that means that the formula will be AgCl. The same thing is going to be true for sodium and nitrate. I'll have a sodium ion get together with a nitrate ion, and so I have to write the formula down. Sodium nitrate. Now, in this particular example, I picked a reaction where all of the ions are have a charge of 1, whether it's +1 or -1. That made writing the formulas easy. So you didn't have to think about anything complicated when it comes to making a neutral ionic compound formula or using the cross-down game, whatever way you like to think about it. But that's not going to be the case every time, and so you're going to have to move a little bit faster, and you're going to have to be able to write these formulas down really quickly. Now, I also want to point out a common mistake. Students get ahead of themselves and start to think about balancing equations before they write the formulas down. Remember that balancing happens after you have the reaction written. If the formula for silver chloride is AgCl, there's nothing that you can do to change the formula for AgCl. So don't start to try to think about how many ions you have before you write down the formulas. And so let's do another example. Let's do something like potassium phosphate plus, let's do lead 2 nitrate. Let's do this one. Okay, so I want to use one more time. I want to color code. This will be the last time I do this though. I want to color code the reactants so we can see A, B, C, and D. One way to look at a double replacement reaction is to say AB plus CD forms AD plus CB. And so remember, we're essentially saying there's a partner and there's a partner, and they swap partners. They go to the swingers club and they swap partners. Nobody? It's one of my favorite chemistry jokes. Man. You lulled? Okay, great. Somebody lulled. Anyway, so we're going to do this double replacement reaction with potassium phosphate and lead 2 nitrate. It's going to be a little bit more of a challenge because the formulas aren't going to be as straightforward. So let's take a look. We want to get lead and nitrate. We're going to identify them. Potassium and phosphate. This is going to lead us to another one of our reaction balancing tricks. Okay, so that means that potassium ion gets together with nitrate ion. And so to make the formula for potassium nitrate, it's just straightforward. It's just KNO3. Okay. Now I've got lead 2 and I've got phosphate. So the formula for lead 2 phosphate is Pb3PO4 2. Nope. Potassium is +1, so I only need 1 nitrate. Potassium is +1, so I only need 1 nitrate because it's -1. So 1 minus 1 is 0. Okay, let's go from there. Now it's time to start to balance. Notice I had the number of ions already. I have different numbers of ions in the formulas, and I have those numbers of ions in the formulas because that's the formula of the ionic compound. Students will often try to say, all right, I need 2 nitrates, so I'm going to do that. But you can't do that because that's not the formula for potassium nitrate. All right, so let's go through this. Now, I want to show you something, and this works for ionic compounds and for situations when you have polyatomic ions that don't change formulas. So let's take a look. I'm going to go ahead and go back to the list. I have potassium and potassium. I have lead and lead. But now I have a choice. I can say I have nitrogen, oxygen, and phosphorus. Or I could say this. I could say, look, let's notice something. Notice that phosphate and nitrate do not change their formulas. It doesn't matter if it's a reactant or as it moves from reactants to products, the formula doesn't change. In other words, there's really no chemistry that's happening to the individual polyatomic ion itself. So you don't have to balance the individual ions or the individual atoms in the ions. You can balance the polyatomic ion as an entire unit. We can balance the polyatomic ion as an entire unit. And this works every time, as long as the formula didn't change. And as long as phosphate stays phosphate, nitrate stays nitrate, you can do this. And so let's count things up. I've got 3, I've got 1. How many phosphates do I have? I have 1 phosphate. How many nitrates do I have? NO3. I've got 2. Potassium, 1. Lead, 3. Phosphate, 2. Nitrate, 1. Let's work on balancing things out now. I just need to move it over just a little bit. Come on. All right. All right, so let's just work on things. Potassium, 3 on the left, 1 on the right. So I can add a stoichiometric coefficient of 3 there. That changes this to 3. But that also changed the number of nitrates that I have. Okay, let's work on lead. I've got 3 on the right and 1 on the left. So I put a 3 there. That changes the number of nitrates. All right, also changes the number of lead. All right, what about phosphate? Well, I've got 1 here on the left, 2 on the right. So it looks like, okay, all right, I got to go back. Oh, man. Now I've got 2, but now I've changed this. All right, well, so let's kind of start over. Let's go back. Potassium. Oops, that's not potassium. I need to go to 6. So that means I need to change this to a 6. And that changed my nitrate. I'm also at 6 there. Oh, look. I'm balanced. I had to work on a particular formula more than once, but that's okay. I mean, that's okay if that happens that way. This gets us nice and balanced in this case. So this is just another trick. You can balance the atoms individually, or you can balance the entire ion as long as the formula doesn't change. Okay. Let's bring in solubility now. Let's bring in solubility. Let's bring back our state symbols. Let's bring back our state symbols. So let's go with sodium sulfide plus let's do, trying to think here. Let's do lead. Oh, we already did lead. Let's do iron 3 nitrate. All right. So what I want to do is I want to switch over and I want to take a look at some solubility rules. And what I want to do is I'm going to look at the actual periodic table that we give you in this course. So, one of the cool things about solubility rules in this course is we don't make you memorize them. And so let me switch my screen share. Let's go back to this periodic table. So this is the periodic table that you should see. Now, what I want to do is I want to zoom in on the solubility rules. Here are the solubility rules. So what I want to do is I just want to show you how it works and how to look at it. There is essentially a line in the sand right here. So we're going to think about above this line and below this line. And so there are 4 rules, but there's an obvious logical cut between rule 2 and rule 3. And so I drew that line. You don't have to memorize the rules, but what you do have to do is you have to be able to use this periodic table to predict whether or not something is soluble. And what I mean by soluble is whether or not its formula, when you write down an equation, will be solid if it's insoluble, or it will be aqueous if it is soluble. And so what we're trying to talk about is whether or not it's going to dissolve in water. Solubility is about whether or not something dissolves in water. What we don't talk about specifically, I'll just mention now in passing, but then we sort of won't mention it again, is that when we talk about ionic compounds and reactions of ionic compounds, they're happening in water. They're happening in water. There's a lot of reasons why that is, and I'm not sure if those reasons are appropriate for the course, but let me just give you one reason. If I want 2 ions to get together to do some chemistry, then they have to touch each other. And if I just mix 2 solids together, then the amount of ability that those ions have to come in contact with each other is limited. If I dissolve them in water, now there's a bunch of ions all floating around each other, and they can come into contact a lot faster. So water speeds up chemistry, especially when it comes to ionic compounds. It's in short, we're talking about a solvent. Solution chemistry is faster than solid state chemistry because the reactants have more of an opportunity to get together. All right, with that being said, we probably won't talk about that particular point anymore. We'll just start to use the solubility rules to determine whether or not something is soluble. So in order to move forward in this discussion, after I'm done with this periodic table and the solubility rules, I'm going to go back to the other screen share so this one won't be up. So if you are watching at home or you're looking at it right now, you might want to go quickly while I'm talking about it, pull up this example so that you have a solubility table that you can refer to while we're looking at the other screen. Maybe you need to look it up on Google, open your book or whatever, download it from Blackboard. Let's take a look at how it works. Okay, so in general, above the line is rules about being soluble. Below the line are rules about being insoluble. That's the natural logical distinction or cutoff between Rule 3 and Rule 2. But let's take a look at it. How do we break it down above the line? In the soluble section, we have two different things. Always soluble, that means soluble all the time, or mostly soluble with some exception. So in rule number 1, there are no exceptions. In rule number 2, there are some exceptions. Now in 3, we get a little bit more less certain of what's happening. In other words, there's definitely always exceptions. So in rule number 3, we're talking about things that are mostly insoluble, that are, insoluble except, and then we give you some exceptions. And then the last rule is just assume everything else is insoluble, okay? But remember that there are exceptions. So let's take a look at what's always soluble to start with. Go back all the way up to rule number 1. So anything that has the cations, sodium, potassium, and ammonium are always soluble, as well as any other cation from group 1. Any other cation from group 1. So lithium, sodium, potassium, rubidium, all of those things would be soluble all the time. What about anions? Any ionic compound, any salt containing nitrate, acetate, chlorate, or perchlorate will be soluble all the time with no exceptions. All right. Chlorides, bromides, and iodides, rule number 2. They're soluble, but there are some exceptions. So when silver ion gets together with chloride, bromide, or iodide, it's insoluble. The same thing with Hg2, and lead 2+. Generally, a chloride or bromide or iodide would be soluble, except with the following exceptions. Right. Fluorides are soluble except with magnesium, with calcium ion, strontium ion, barium ion, and lead 2 ion. Okay. Sulfates are generally soluble. Sulfates are generally soluble except with these 3 cations. So sodium sulfate is soluble, but barium sulfate is not soluble. Remember, if it's soluble, then it's dissolved in water. That means that the formula, the state would be aqueous. If it's insoluble, it means it won't dissolve in water, so the formula will be solid. All right, so let's take a look at mostly insoluble. Salts containing hydroxides are insoluble, except for if it's got a cation that's always soluble. So Even though most hydroxides are insoluble, sodium hydroxide is always soluble because of rule number 1. The same thing with potassium hydroxide, always soluble for rule number 1. In addition to that, calcium hydroxide, strontium hydroxide, and barium hydroxide are soluble as well. So this is how you use this table. And so what I want to do is I want to stop sharing this table. I want to go back to the other screen, and I want to fill in the states on that reaction that we were working on. What about sodium sulfide? Is this soluble or insoluble? Soluble or insoluble? Yeah, sodium, right guys, is always soluble. So the state on sodium sulfide is aqueous. The state on sodium sulfide is aqueous. What about iron nitrate? Soluble or insoluble? Nitrates are always soluble. Yep. Nitrates are always soluble. So I'm looking for something that I can apply a rule to. And the first thing I have sodium ion. Sodium is always soluble. So I can apply that rule to it. And the second thing, iron nitrate, I have a rule for nitrate. Nitrate is always soluble. So I can apply a rule to it. So now we have to combine creating formulas and applying solubility rules. We have to do all of this before we balance the equation. So let's take a look. I'm going to have sodium ion get together with nitrate ion, and so that forms sodium nitrate. Is that soluble or insoluble? Well, sodium and nitrate are always soluble, so it's aqueous. What about iron 3 and sulfide? The formula will be Fe2S3. Is it soluble or insoluble? Well, on that sheet, there isn't a rule about sulfides. Actually, sulfides do the same thing as oxygens, or they do the same thing as hydroxides. But even if you didn't have that particular rule, you would assume everything else is going to be insoluble, and that's the case here. This is not soluble. This is insoluble, so it is a solid. Okay, that's the job that you need to do when it comes to completing the reaction. Not only do you have to predict the formulas by using your nomenclature skills to create the formulas of ionic compounds, but now you also have to write down the states. So this brings in an extra level. So you have to decide whether it's soluble or insoluble. Okay, let's take a look now. Let's do the balancing part. So let's see, 2 sodiums, 2 sodiums, good to go there. Iron 2, oh, I got 2 irons, so that goes there. Oh man, now I messed up mine. Oh boy. Well, I got, whoa, 2 irons, 2 irons. What about sulfurs now? 3 and 3. Okay, that messed up my sodium again. See how this works? So now we're going to recount sodium. 3 times 2 is 6. Okay. Let's do 6 there. So now I've got 6 nitrates. Let's do, oh, okay. 6 nitrates on the right, 2 times 3, that's 6 nitrates on the left. I'm okay. Okay, so that's not true actually. The acetate for rule number 1 is on the periodic table on Blackboard. I did just show that to you. Okay, so let's just real quick pull that. All right, so yeah, I'm hoping that, because then we should be right here, right? Because this is the same formula where we left off with. So welcome back to the recording. I know that was a hard break. Maybe that was confusing. So now you have to look at two different videos, part 1 and part 2. And so this is where we're at. We're back with this particular ionic equation. We wrote down the full and balanced the full and balanced molecular equation. That's what's at the top. We were talking about what the complete ionic equation is. We want to be able to write that down and talk about what it is. What it is the description of ions in the solution as they actually exist. So what I was talking about, and what you see written at the bottom of the screen as if it magically appeared, is the formulas, the equations representing taking a solid and dissolving it in water. So if I take an ionic compound and dissolve it in water, then the individual ions themselves become solubilized and they are actually aqueous. So this is what it means. An ionic compound breaks up into its individual ions when it becomes dissolved in water. So if with sodium chloride, I would have 1 sodium ion and 1 chloride ion, but with sodium sulfide, I have 2 sodium ions and 1 sulfide ion. And so I'm going to apply this same bit to the equation above in order to write the complete ionic equation. Since I've written the complete molecular equation and I've balanced it, writing the complete ionic equation is relatively straightforward from that point. What I do from that point is I use the balanced complete molecular equation to construct the complete ionic equation. There's no hydrogens in this. The question is, it won't make a compound with hydrogen and oxygen, question mark. There are no hydrogens in this formula, so I don't know where they would come from. There's no hydrogens in this equation, so I don't know where you're going with that. So remember, we're not just going to start adding atoms to equations, because that's a different chemical reaction, and we're always I see. No, no, we're not talking about reacting with water. So no, I got you. Yeah. All right, so let's take a look. Constructing the complete ionic equation is deconstructing the complete molecular equation based on the states. So watch how this works. Let me break up the sodium ions. I have 3 sodium sulfides, so that means I have 6 sodium ions, and they're aqueous. I have 3 sulfide ions, and they're aqueous. I have 2 iron 3 ions, and they're aqueous. I have 6 nitrate ions, and they're aqueous. That's how I deconstruct the equation. Notice that I write the charges. A common mistake students make is to leave those charges out. They need to be in place. We're talking about ions, and ions have charges. So deconstructing the products, 6 sodium ions, aqueous, 6 nitrate ions, aqueous. Now what about this last product? The last product is a solid. Since it's a solid, the ions are not aqueous. They're not separated from each other. They have not disassociated. So for pure solids, pure liquids, and pure gases, I write down things exactly as they appear. So for the iron 3 sulfide, I just write down Fe2S3 solid. I have now written the complete ionic equation by deconstructing the complete molecular equation. All right, let's do the the net ionic equation. I write the net ionic equation by canceling out anything that appears on both sides. Anything that appears on both sides in exactly the same quantity and state will not be included in the net ionic equation. They are what we call spectator ions. They don't do any chemistry. They just stand around and watch. Nothing happened. These are the spectator ions. The net ionic equation is what will be left. 2 iron 3 plus aqueous plus 3 sulfides aqueous form Fe2S3 solid. This is the net ionic equation. It describes the actual chemical changes from aqueous to solid based on our solubility rules. This is what actually happens. Okay, so what you have to be able to do, there's a lot of things that you have to be able to do. So let's back it up. You have to be able to take a set of reagents, AB plus CD, and you have to be able to predict the formulas, AD plus CB. You have to write those formulas down. Then you have to balance them, X, Y, Z, Q. Then you have to predict the states by using the solubility rules. Then once you have the complete molecular equation written down, you have to deconstruct it into a complete ionic equation. Then once you have the complete ionic equation written down, you have to be able to identify the spectator ions. In other words, cross out things that appear exactly the same way on both sides of the reaction, and then write down what's left to get the net ionic equation. Let's go back to an equation that we did before. We did it before. We didn't have any states written down, but now we have enough information to write down states. Sodium chloride plus silver nitrate. What are the states? Sodium is always soluble, so that's aqueous. Nitrate is always soluble, so that's aqueous. Sodium nitrate is always soluble, but the other thing is silver chloride. And if you take a look at the exceptions, for chloride, chloride is generally soluble, but one of the exceptions is silver. So it's solid. The question is asked, will this be in all reactions or just double displacement reactions? Double displacement reactions are the only reactions that you will use to write complete and net ionic equations, with the exception being acid-base reactions, which we'll discuss in just a second. When it comes to acid-base reactions, we think about them slightly different than being double displacement reactions, but they are essentially a double displacement reaction. So back to this one. Again, we know I chose this one because everything was 1-to-1, and so this equation is already balanced. But now if I wanted to write down the complete ionic equation, I would write down sodium aqueous plus chloride aqueous plus silver ion aqueous plus nitrate ion aqueous yields sodium ion aqueous plus nitrate ion aqueous plus silver chloride solid. So what are the spectator ions in this case? What are the things that appear the same in the reaction? So the spectator ions are sodium and nitrate again, just coincidentally the same two ions. So what's the net ionic equation? Silver ion aqueous plus chloride ion aqueous produces silver chloride solid. Okay. Well, let's do that acid-base business now. There's one more type of reaction that you have to complete, the acid-base reaction. And this is how acid bases work. Acid plus base produces water plus salt. And remember, salt just means ionic compound. Now, you already know how to identify acids. You already know acids. What about bases? In this class, a base is an ionic compound with hydroxide in it. It's that simple. So bases in this class are hydroxides. Bases in this class are hydroxides. So the base will be something like sodium hydroxide or calcium hydroxide or one of those other hydroxides. All right, and the products will always be water and some other salt. What is the salt that I mean? Well, an acid is something that has a hydrogen ion in it. And if a base is hydroxide, then water is one of the products, and so is some other salt. Well, what's the salt going to be made out of? It's going to be made out of sodium. Well, in this case, it's sodium, and in this case, it's chlorine or chloride. So the salt in this case is sodium chloride. This really is just a double replacement reaction. Here are the partners that swap, and here are the partners that swap. It's just that when you put together H plus ion with hydroxide, you don't get an ionic compound, you get water. When hydroxide and H plus come together, you get water. So it really is at its heart still a double replacement reaction. But we use this mnemonic to memorize how to complete the reaction. So acid plus base yields water plus salt, but at the end of the day, it really is just a double replacement reaction where H plus and hydroxide form water. So let's go ahead and let's try some of these reactions, and let's do complete and net ionic equations for it. So let's do an example. Let's do calcium hydroxide this is taking too long. I'll just rewrite it. Calcium hydroxide plus let's do HBr. Right. We look at the solubility rules and we can determine that calcium hydroxide is aqueous. And so let's now write down our products. Well, one of the products is water, but remember, water is not an ionic compound. So we'll write down liquid. What's the salt? The salt will be formed from bromide and calcium. And so that's Ca2 plus and Br minus. So the formula will be CaBr2. And if I take a look, this one should be aqueous based on the solubility rules. Now that we've written down the complete formulas, we've completed the equation, we've written down the formulas, it's time to balance. So I've got 2 bromines, so I need 2 bromines here. It looks like everything else is balanced except for the hydrogens and oxygens. So I have 2 hydrogens plus 2 hydrogens on the left, so 2 here, 2 here, that's 4 total. So I need a 2 here to balance out the hydrogens, and that should also balance the oxygens. 2 here, and now I have 2 there. So the oxygens are all balanced. So how do I write the complete ionic equation for this acid-base reaction? Well, I've got a calcium ion, and it's aqueous. And I've got 2 hydroxide ions, and they're aqueous. Remember that the parentheses and the stoichiometric and this factor outside of the parentheses, I almost called it a stoichiometric coefficient. It's not a stoichiometric coefficient. It's just part of the formula. The 2 in this formula indicates there are 2 hydroxide ions. Now, what about the acid? Well, remember that the acid is a molecular compound, but that it behaves ionically. And so instead of writing down HBr together, it is aqueous in this case. It did behave ionically when you put it in water. So it broke up into H+ ion and bromide ion. And that produced 2 waters. Water is a pure liquid. It is not broken up. So I write down pure liquids and pure solids and gases exactly as they appear. And the same thing now over here, Ca2+ aqueous plus 2 Br- aqueous. Let me spread that out just a little bit. Now the net equation. Let's find out what the spectator ions are. It looks like calcium and bromide are spectators. Calcium ion and bromide ion, they're the ones that appear the same on both sides of the equation. So let's write down what's left. H2 plus 2H2 plus, excuse me, let me try to say this correctly. 2 hydrogen ions plus 2 hydroxide ions, both in the aqueous phase, come together to form 2 water molecules in the liquid phase. So this is the net ionic equation for acid-base reactions. At the end of the day, hydroxide plus H+ forms water will always be the net equation for an acid-base reaction. The only question is, what will the stoichiometric coefficients be? So this is it for, I want to just stop for a second and kind of wrap up acids and bases there. They really are just double replacement reactions. But instead of producing 2 ionic compounds, one of the compounds that it produces is water. So this is what we mean by a neutralization. We mean that something that was an ion is neutralized into a neutral molecular compound. Does anybody have any questions about that? I just want to stop for one little beat. All right, let's go back to I just want to create just 2 more examples. Let's go with potassium iodide plus lead 2 nitrate. Let's do everything for this one. What are the states? Potassium is group 1, so it's always soluble. Nitrate is always soluble. The partners are going to swap. Potassium nitrate, KNO3, still soluble. Lead 2 iodide is PbI2. Iodine is generally soluble, but one of the exceptions is lead 2. So it's going to be a solid. Now that I've written the equation down, let's balance it. So I need 2 iodides and I need 2 potassiums and 2 nitrates. And now I'm balanced. The formation of a solid is called a precipitation reaction. So we've discussed these types of reactions before as it relates to solubility rules, but now I just want to give a name to it. So anytime 2 aqueous ionic compounds come in contact to form a solid ionic compound, then that is a precipitation reaction. But we're going to do everything else the same way. We're going to say 2 potassium ions plus 2 iodides plus 1 lead 2 ion, all of these aqueous, 2 nitrates, produce 2 potassium ions aqueous, 2 nitrate ions aqueous, and then lead 2 iodide solid. What are the spectator ions? Potassium and nitrate appear both sides. We'll cancel those out. We'll label them as spectators. And then we'll rewrite everything else. Pb2 plus aqueous plus 2I minus aqueous produces PbI2 solid. That's the net ionic equation. Right. Precipitation reactions involves 2 aqueous ionic compounds forming a solid. That is a precipitate. The precipitate is the PbI2 in this formula. All right, the last bit, and it's just sort of like a little bit of housekeeping, is I want to just define gas evolution reactions. I just want to define a gas evolution reaction. So you're not necessarily going to be able to necessarily predict in this particular case. But if I give you this type of equation, right, H2CO3 aqueous produces H2O liquid plus CO2 gas, you should still be able to balance it. It is balanced in this case. But look what happens. Something that's aqueous produces a liquid and a gas. If there are more molecules of gas in the products, then this is a gas evolution reaction. So you don't necessarily need to be able to predict the products like you would in a combustion reaction or an acid-base reaction or a double displacement reaction, but you do have to be able to identify it. You have to be able to identify the type of reaction, based on the question, is there more molecules of gas in the products? If the answer is yes, then you can call it a gas evolution reaction. Now, sometimes reactions will fit more than one description. This is a gas evolution reaction, but what else is it? What other description does it fit? Decomposition. Absolutely. So this is also a decomposition reaction. And so you need to be able to identify them in several different ways. And one of the ways is gas evolution, acid base, combustion, but you also need to be able to identify them in the four basic senses. Is it decomposition? Is it synthesis or combination? Is it single displacement or double displacement? And so that's all the things that you have to be able to identify. And so we've talked about net ionic equations. We've talked about complete ionic equations and how we can write those down from complete molecular equations. We've talked about the different types of reactions, how to identify them, how to write them down, how to predict the states of different products, how to predict the states of different reactants using solubility rules. And so it is not based on, so the question is asked, what do you mean by more molecules? Is it based on mass? Well, let me kind of ask you that question in reverse. Does more molecules, is that based on mass? More molecules is a what? What am I asking you about? Am I asking you about how massive they are? I'm asking you how many there are. And how many is not in all based on mass when it comes to counting the number of molecules. One molecule on this side, two molecules on this side. That's how we decided after it's balanced. Absolutely, after it's balanced. This is one molecule on the reactant side, two molecules on the product side. That's how we decided it was decomposition. This molecule is aqueous. This one is solid. This one is gas. We have 0 gas molecules here, and we have 1 gas molecule here. There's more molecules of gas in the products, so therefore it's gas evolution. That's what we mean by that. So at this point, we have completed all of the work that we want to do with chemical reactions. So I'm going to stop it there. This video is going to be a little bit of a two-parter.